We will begin this demo by compiling the server-side code. This can be done with the following GCC command. The only standout feature in this is that you must include the curl library at the end of the arguments, or else you cannot calculate the bandwidth that the server is running on. So we can see that it downloads an HTML file from example.com. You can see below that this is an open source document that you can download to test out a really quick download speed. This is running on the OSU servers, and you can see at the time that it got 69.2 megabytes per second. The server is now waiting on port 8080. And so we can go over to the client-side code now and compile that with the following GCC command. Once we run the client, you can see that it asks the client how many bytes of data it would like to download. We can also see that once it connects to the server gets a new connection message and displays the port that the client connected on. So for this demo, we will begin with 1, 2, 3, 4, 5 bytes requested on client 1. We can see over on the server side, this is the first client that was connected. Now that the client is connected to the server, we can see that the client 0 requested 1, 2, 3, 4, 5 bytes, and we have a total bandwidth of what we calculated before. Down below we can see our first calculation. The standard TCP connection would have given 100% because this is the only user, and we can see that that's the case for all of these. It should always give the single user full bandwidth and 100% of it. Now we can connect in with the second client. And we will request 5, 4, 3, 2, 1 bytes. So now that we are connected in, we can go back to the server side and see that there are 2 clients. There was the last request from the new client, and here's the new calculations for the 2 clients. The TCP connection would have been 50-50 with the 2 clients, and this is where you can start to see the difference in our weighted connection. Our weighted connection would have given user 0, who was requesting significantly less bytes, 18.52% of the bandwidth, and user 1, who was requesting significantly more bytes, 81.48% of the bandwidth. We can see down below that the fair calculation is the exact same, and we will get into why this is the same later on. Now with the second client connected, we can begin to check the edge cases by using a third and a fourth client. We will begin by starting with a really small amount of data, just a single byte. So we can see back on the server side now that client 2 requested a single byte. We can see that the standard TCP connection would have given each of these users an even third of the bandwidth. Our first implementation would have given the third user what they say is 0%, but it's literally just such a small percentage that these 2 floating points can't pick it up. Now the fair allocation down below is where we give the user the bandwidth that would be given to a standard TCP connection if the maximum amount of users were connected. So with 30 users connected, we roughly get about 3%, so the threshold of 3% was set for the fair calculation. If, say, 100 users were used in this server, we could scale this so that 1% would be the fair bandwidth allocation. But we can see that compared to above, it took the 3% away from the highest downloader. So if all users are connected in with a fair connection, they'll all get 3%, and it'll still be the same as the TCP fair allocation. However, if there's less than the maximum amount of users connected, we do the kind of same weighting that we would on the earlier calculation. We can test another edge case by using the fourth client. And we will begin by connecting in with an exceptionally large data value, larger than anything else has requested. Now, while this might look like an issue down on the bottom, initially, each user that is given below the 3% allocation is given 3%, and these trickle-down numbers I ended up going back through and leaving or putting back in because these are recalculations of the entire weighted tree after subtracting out the 3%. So you can see here, even though they won't get 0.10% here, they're going to get the 3% plus the 0.10%. So user 0 will actually end up with 3.1%, where user 1 will end up with 3.4%. Another feature of this dynamically weighted tree is that whenever a user leaves, let's say user 3 here, the server recalculates the tree. So where we can see that before user 1 was only given 70%, we are now back to 81.48%. Now looking at a brief overview of the code, we'll begin with the multiserver.c. It's titled multi-server because our initial one was just server, but that only allowed for a single client connection, so a full revamp of the server was necessary within the last week to accommodate all of the users. We begin with a simple get bandwidth function. This is done by downloading an HTML file that's really basic from example.com. This is an open source website that you don't need to get permission from before. Until I found out about the curl library, I was unable to get this accomplished, but luckily after I found that out and a couple Stack Overflow references, that's how I was able to get the bandwidth downloaded. Next we have the current users. This just returns a simple int of how many users are connected to the server at a given time. Usually the buffer would always read 30, but this goes through and double checks that the number is either accurate or less than that. This is used to calculate the basic TCP bandwidth that would be allocated to each of the users. It's a lot more basic than the rest of them because you can just simply divide the total bandwidth by the amount of users that are connected and simply multiply that by 100 to get a percent. This was initially our idea of implementation for a weighted tree distribution. It has no fairness built in and is a pretty aggressive weighting. If one user did request infinitely more data than the others, it could theoretically take 100% of the bandwidth from the server. So this would be one feature that might be a problem in the real-world implementation, and we will get to that later on. This is simply done by doing a weight calculation where the total bandwidth is divided by the total amount of bytes that all the users requested. So you can get a number that is the bytes per second per byte requested. And that was how we were able to create our dynamically weighted tree. Further down, we see the fair calculation. This was a hybrid of the standard TCP implementation and our aggressive weighting that we thought would work a little bit better in the real world situation. But all that this does is it checks to see that a user is given more than the lowest amount that they would be given on a TCP connection. So for this one, that is 3% of the total bandwidth because we have a limit of 30 users. So this could be changed around, and these numbers are something that I'd like to get more dynamic for future settings, and so that the entire server could scale to hundreds if not thousands of people. Down here we end up doing roughly the same calculation of up here, but the difference is that I found out later on that I would have to go through the entire list twice, simply because I would need to subtract out all of the less than 3 bandwidths. So after doing all of the less than 3% of the total bandwidth calculations, we go down and we allocate the rest of the bandwidth. Down in the main, we have a pretty simple setup for a server and client connection, socket connection. I'm sure you've all become familiar with this over the last couple years in assignments, so I'll glance past that. And once we get into our infinitely running loop, this is where we really start to see our server code. So we begin by adding the new connections underneath this functionality. And once we get past all of the error handling for adding a new connection, we can see this is where the new connection begins. We begin by reading in the requested amount of bytes from the user. This will always stay the same, but what I hope to do is later on make this a dynamic number on the client side, just to automatically send. Once we get down into adding into an array of sockets, we can start to see a few little weird things. This is where I had to remove end line characters and convert from a string input over to a integer. After that, we can begin the calculations for the current users, the regular TCP connection, our very aggressive weighting, and the fair calculation. Below this, we can see the rest of the I/O functioning that is used for the client-server communication. I left the echo in here because I will use this for future expansion and communication between the server and client. Up above here, we do a calculation to see if the client is still connected, and if they're not, we set their socket equal to 0 as well as the data requested, and then we go back and we recalculate all of the bandwidth allocations. Now looking at the client side, we have a very simple structure so that we can connect into the server and send over the amount of bytes that we request. The entire sending is handled by this function, and all it asks is for you to manually enter the amount of data in bytes. If you don't enter just pure integers, you get no bandwidth. I made sure that it would still work and it doesn't break the server, but if you misuse this, it doesn't work. This is something that I could fix later on to keep asking for a bit until you only enter integers. We can see that the buffer is compared to exit to see if either the client asked to exit or if the server had sent over an exit message. And we double check the amount of bytes entered. This is the same standard structure to connect into a socket, and once the connection is successful, we run the function to send the amount of bytes, and we wait to hear back from the server. A few things that I'd like to expand further on would be edge cases, so that if large amounts of data are entered, it doesn't seem to have such a struggle recalculating everything. I'd also like it to do the bandwidth calculation, but for the amount of packets being pulled down on the client side, and I'd like that to be automatically sent over so that a YouTube video could be watched on one client and another one could be trying to download a text file, and the correct amount of bytes being requested would be sent over to the server automatically. Another thing I hope to build in is file structures and file downloading so that this could be used on, say, a Pi-hole or on a kind of personal network if any kind of internet outage should occur.